Afternoon and welcome to the second invited lecture in the field of chemistry and chemical physics. My name is Karolis Kazlauskas. I am from the Institute of Photonics and Nanotechnology at Vilnius University, and it's my great pleasure to introduce Dr. Andrew Poon from the University of California, San Diego. He will talk about a fascinating phenomena about incoherent photon upconversion mediated by triplet annihilation in smartly designed organic systems, which offers a wide variety of interesting applications, including photovoltaics, photocatalysis, 3D printing, etc. So, as the title suggests, the focus will be on novel annihilators, which opens a new possibilities for applications. I prepared a few facts on Andrew's background. So he received his bachelor's degree in chemistry from the University of California, Berkeley in 2013. Then did a Ph.D. at Columbia University. After that, obtained postdoc at ETH Zürich. And currently he is an assistant professor of chemistry and biochemistry at the University of California, San Diego. So, Andrew, the floor is yours.
Thank you. So again, thank you to all the organizers and for inviting me to this talk. It's been a really great time seeing Lithuania, seeing the facilities here. Overall, been a great visit so far. So as has been mentioned, my talk is going to be focusing on new applications of triplet upconversion via exploration of novel annihilators. Here in the background is the famous library at my university. We host lots of conferences ourselves in our, can you hear that? Okay. In our large convention center in San Diego. So if you ever get a chance, please come say hi and you can see our nice library as well as our nice weather. So to begin with, what is triplet annihilation upconversion? I think this institution is quite familiar with this process. It's a very nice process because we can tell very easily when it's happening. So if you look on this, my right, where's the laser pointer? There we go. Yeah, so over here we can see upconversion happening in solution, where we're going to convert low energy light or longer wavelength light into high energy light. So in this case, green to blue, done in solution in a vial. And on the other side, we can see this done in a film where infrared light, which we can't see, turns into visible red light. And so there's various mechanisms by which upconversion can occur. And the one that I'm most interested in is this triplet annihilation upconversion. This process requires two species, a sensitizer, which absorbs low energy photons, transfers that energy to an annihilator, which emits high energy light. This process has been studied very heavily over the past couple decades because it can occur very efficiently at low input flux. So you can see here, I think they just used a regular old green laser pointer to excite this. And you can actually measure this experimentally and see that upconversion with this mechanism starts to be very efficient, even at very low power densities. So here the excitation density is at milliwatts per centimeter square. Just for reference, solar radiation on a sunny day is around hundreds of milliwatts per centimeter square, depending on the wavelength you're looking at. So what this means is that because we can do upconversion efficiently, given judicious choice of annihilator, sensitizer, and the correct system, we have this gigantic application scope that we can use triplet annihilation upconversion in. So the application that's gotten the most focus definitely has to be making more efficient photovoltaics. So if we look at this graph here tells us how efficient a solar cell can be given the band gap energy. So on that x-axis is the band gap of any given solar cell, And actually, the maximum efficiency of a conventional single junction solar cell is only that deep blue area of the curve, right here. So even the most efficient solar cell can only be right around 33% efficiency. So only 33% of the energy that's given off by a light source like the sun can be converted to electricity. There's a lot of energy that's lost. So in particular, what we are interested in upconversion is taking advantage of all this pink energy right here, this energy that's below the band gap. So another way to think about that is if you look at this diagram, here we're looking at a conventional silicon solar cell, and on top of it is overlaid solar radiation in Boulder, Colorado, or Golden, Colorado. And so we can see here in yellow, with a perfect silicon solar cell, we're going to be converting this portion of the solar spectrum efficiently into electricity. But there's all this other source of wasted light. So we have wasted light here due to extraction, wasted loss here due to thermalization, and wasted energy here due to photons that are below the band gap of your silicon solar cell and therefore not absorbed. So with upconversion, we could convert these photons into usable photons to then make a more efficient photovoltaic. The way that would look would be something like this. You can imagine you have a solar cell here, and we're going to have photons, white light come into the solar cell. The solar cell is going to efficiently turn blue, green, and yellow light into electricity, whereas longer wavelength photons are just going to get transmitted through the solar cell. If you then had some upconversion layer below the solar cell with something like a mirror below it, they would then upconvert photons back into something like yellow photons, which would make their way to the solar cell and then be efficiently converted into electricity. There's various strategies to do this. You could look at something like other wavelengths of light, such as turning infrared light back into red light to do this upconversion process. But this is the general mechanism to make a more efficient solar cell using upconversion. And you might be asking, why aren't we doing this yet? And unfortunately, even with the most efficient annihilators and sensitizers that we have available to us, we're only going to make very minuscule changes in efficiency. So you can see here in this graph, they showed as a function of wavelength, how the quantum efficiency changes, and this y-axis is 10 to the minus 2. So you're making a very, very tiny change, a perceptible change, but it's one that's very tiny. So in order to move forward, we need to make new materials and have better engineering so that we can realize the potential of upconversion in photovoltaics. However, one of the things we see here is how we can turn what the maximum efficiency of solar cells would be given a triplet annihilation upconversion enhanced photovoltaic. So in black here is the thermodynamic limit, and in black here is the limit for solar cells as a function of their band gap if we're using an upconversion layer. And those colored points that you see are how high that's actually given the current solar cell technology we have. So for example, gallium arsenide solar cells in this red diamond here, gallium arsenide is quite efficient, so we can get quite efficient using upconversion. However, again, there is an issue, and that is that at present, we can really only efficiently do triplet annihilation upconversion using energy that is input of around 1.5 eV. So what that means is that all these photovoltaics over here to the left side of this graph, over here, we can't really access. And over there on the left, you see things like crystalline silicon, gallium arsenide. So we really need to expand the scope of upconversion to push us towards these redder materials to make more efficient photovoltaics. And so I've been talking about photovoltaics for a long time, but I should mention that there's many, many other applications of upconversion. Just to name a few, one that's being looked at now is to look at for infrared imaging. So people have thought about using upconversion in order to convert invisible infrared photons into visible green photons, for example. This has been shown a couple times. However, in both of these existing systems, you have to apply an external electric field. And so the dream of using upconversion would be to have an all optical device where you just put infrared light in, and then you can detect it as visible light. Other applications, some fun ones include anti-counterfeiting. So for example, here, you can pattern some sort of film that does upconversion. And then you can do dual patterning. So here in the bottom left, you can see they've done some sort of hash marks in a fluorescent material, whereas the QR code is only visible with upconversion. So if you use a regular fluorescent light, you're not going to be able to detect your QR code. However, if you use infrared light, or 635, so red light, you can actually see the QR code. So you can do this for some sort of interesting anti-counterfeiting, or combine it with delayed fluorescence or phosphorescent materials to do some sort of interesting cryptography type work. And that's just a couple. There's many, many more. There's recent work with 3D printing, a lot of work with biological imaging, stress sensing with this, and many, many, many more. So I, as a chemist, think about how I can improve this field that's pretty much dominated by physicists and engineers. To me, I think, why don't I make new materials that are better than the existing ones we have? So I mentioned before, there's two main classes of materials that are used in upconversion. We have sensitizers and we have annihilators. So there's been a lot of recent work done on sensitizers. The original work focused on these metallated macrocycles like that platinum complex up in the top left. And a lot of work's now being done on semiconductor nanocrystals as sensitizers. However, if we look at the literature, 90% plus of the work is being done on these acene derivatives here. So these anthracene and tetracene derivatives that have been functionalized a little bit. They're very efficient. There's a lot of research done on these organic crystals. However, there are some pretty big drawbacks in my mind. First off would be that these are very unstable. So if you look at anthracene, it's known to photodimerize. Rubrine's even more notorious for being very unstable. So rubrine will very readily turn from this brilliant red fluorescent solution and then oxidize irreversibly in the presence of oxygen. And so you can imagine if we have these species that we want to use for some sort of light-based applications, they probably shouldn't be photosensitive. We should develop materials that can survive light to use in the light. So to go through the mechanism of conversion, again, I suppose, again, we need two systems or two species, a sensitizer and an annihilator. The sensitizer serves to first absorb low energy light, like so. From there, your sensitizer will be populating its first excited singlet state. This sensitizer should have some sort of ability to undergo intersystem crossing efficiently to generate a first excited triplet state. This can then undergo some sort of energy transfer to populate a triplet on your annihilator, from which point two of these annihilators in their excited triplet states meet, undergo triplet-triplet annihilation. In this process, no energy is lost, or energy is conserved, and we generate a singlet in the ground state as well as a singlet in the excited state. And this higher energy singlet can then just decay via fluorescence, giving you that higher energy photon out. So while there are many moving parts in this mechanism, energetically speaking, in terms of how we need to design our molecules, the design rules are actually quite straightforward in my mind. So first of all, we need to have a sensitizer triplet higher than the annihilator triplet, just so that this energy process from here to here is thermodynamically allowed. That's not a problem, because we can pick any given sensitizer to match any given annihilator. The other thing that's actually more intrinsic to the material would be this second requirement here, where the annihilator triplet has to, when these two combine, that energy has to be greater than the singlet, just so that when you do this TTA process, this energy combined can be enough to populate this state. Another important measure or figure of merit in upconversion would be the anti-Stokes shift. So that's just going to be the difference in energy of photons out compared to the photons in. So for example, here would be subtracting the energy of the blue photons by the red photons. And you can imagine in upconversion, we really want to expand this number to have a really big dynamic range of upconversion. So the first story I'll tell about designing new annihilators for upconversion is going to focus on this molecule here. It's called diketoperoleperol, also known as DPP. And so what got me interested in this back when I was in my PhD was this paper from the Wasilewski group at Northwestern, where they reported the triplet energy of this. But they reported several derivatives of this DPP, and they noted that the singlet energy doesn't change. So the singlet energy changes, whereas the triplet energy doesn't. So you can change the molecule, add these phenyl groups, these thiophene groups, longer appended pi groups, and that leads to a change in the singlet, whereas the triplet stays pinned. So to me, I thought that means we can take advantage of this and make a molecule that has these desired energetic properties to undergo triplet-triplet annihilation. So what we did was we got in the lab, so we took this DPP and then changed the pi groups that are pendant on it. So go from a phenyl group to a furan group to a thiophene group. And from here, we could extract the singlet energy quite easily just from UV-Vis optical absorption spectroscopy. And then we can make a very, very simple energetic picture like this. So given that the DPP triplet is 1.15 eV and stays at this energy, when we get TTA, we should have two of these triplets. That should give us 2.3 eV. And so that energy has to go downhill. So therefore, if we're going to populate a singlet, it can only have a singlet energy lower than 2.3 eV. So these two black lines add up, and then that energy needs to go downhill to populate the singlet. So that would tell us that the phenyl group should not serve as an annihilator, whereas the phenyl version and the thiophene version should. And gratifyingly, that proved to be the case. We went to the lab, and only these two worked. And so 3 data points is nice, but one of the great things about this DPP molecule is it's been widely studied for the past couple decades, and you can readily make a variety of different derivatives. All these derivatives took me about 5 days to make. And then from there, we can go ahead and do optical spectroscopy again, just absorption. We have this nice continuum of species as their single energy is decreasing. And again, we could just draw a straight line, and here, that's going to be 2.3 EV. That's going to be the energy we get from TTA. And again, the requirement for triplet fusion or triplet annihilation is that the triplet, double the triplet has to be more than the singlet. So basically, anything to the right of here has a singlet below 2.3 EV and should function as an annihilator. Everything to the left shouldn't. And that proved to be the case. So all these different species could serve as annihilators. So what that told us was, first off, we can develop new families of annihilators quite quickly with these really relatively simple energetic design rules. And also, one nice thing that I haven't mentioned is that DPP is very, very stable. Ferrari actually uses it in car paint, so bright red Ferraris are actually using a derivative of DPP. This is an extremely stable pigment as opposed to rubrine. So in addition to developing stable materials, we thought stable and new materials, one of the other things we were interested in as chemists was how we can tune existing materials and discover some sort of design rules to make better annihilators. So one thing we looked at was the mechanism of triple annihilation itself. So first off, again, we have this process where we're going to populate triplets on our sensitizer. But then after that, we do these multiple steps where we populate triplets on the annihilators. These undergo triplet fusion or triplet annihilation, generates a singlet, emits. And one thing that we noticed was that we have the key step of triplet annihilation, also known as triplet fusion, here requires 2 of these annihilators in their triplet states to meet. Okay, we need 2 excited triplets to meet. And we thought, okay, instead of having to focus and wait for these 2 things to diffuse in solution and meet each other, why don't we just link them together? If we could just dimerize these things, they'd be primed to do triplet annihilation. We wouldn't have to wait for this. So that's what we did. We went and did these tetracene derivatives. So top left is just monomeric TIPS tetracene. On the right is the sensitizer that we used. And on the bottom is these different dimers we used. And so we started out with just basic bitetracene, where we've linked 2 tetracenes together. And then we used different phenyl spacers to see if there was some sort of effect that spacing these out would have on the triplet annihilation process. We also ran some pretty straightforward DFT calculations to calculate where the triplet wave function should sit. So on the left-hand side, you have the directly linked tetracene dimer. And you can see that while the triplet wave function is highly localized on one monomer, it does leak out a little bit onto the second tetracene monomer. In the case of the 4-phenyl linked bitetracene, you do see this leakage, but it's only onto the phenyl bridge. It doesn't make it all the way to the other tetracene. So what that told us was that if it's sufficiently close together, we think that this intramolecular triplet annihilation would lead to an enhancement of our upconversion, whereas as we space it out, this would become less and less of a positive factor. So what we could do here is measure upconversion photoluminescence as a function of the concentration of the annihilator. And you can imagine in the case where you need 2 annihilators to meet, as the concentration goes lower and lower and lower, this process is going to rapidly become less and less efficient. If there's less of them around, they're not going to find each other unless they're directly linked. So you can imagine that as the concentration goes down, we would imagine that this is going to have less of a deleterious effect if they're linked together. And that proved to be the case. So if you look at the black trace, that's the monomer, there's a very, very dramatic decrease in upconversion efficiency as you decrease the concentration. So going down 1 order of magnitude in concentration from the far right to the far left, we see a more than 1 order of magnitude decrease in our upconversion photoluminescence. And if you look at our optimized bitetracenes, such as the bitetracene 1 or bitetracene 2, we see actually only about a 2- or 3-fold decrease in photoluminescence as we decrease the concentration so dramatically. So this told us that we can optimize materials for low concentration applications by doing this, but also that there are design rules that we can tease out just by simply modifying our chemical structure, which is something that we think we can uniquely bring to the field as chemists in this highly engineering or physics-based field. So this was work that was done in my PhD along with Luis Campos and Dan Congreve, my advisors. But I'm happy to present a story that's actually come to fruition in my independent career in this past year. So this is kind of merging both topics from before, looking at new materials, as well as optimizing materials and developing some design rules. So for this, we focused on this molecular core. This material is called dipyrrolonaphthyridine dione, or DPND for short. And that DPND is just this simple base molecule here. The R groups mean just an alkyl chain, a solubilizing alkyl chain. So we can either have the alkyl chains linked to either side of the molecule, or they could be linked together to make this sort of strapped bridging motif, like a cyclophane. The synthesis is quite straightforward, and you can also derivatize it quite readily from this chemistry that was developed in the Greco group in Warsaw. And so you can readily append aryl groups onto it in one step. So what we did that also made us think that this material could be a good option for upconversion was we looked at this work from the Fu group in China, where they saw the optical properties of this material. And so they noted that in solution, this material had a very efficient fluorescence, and they measured the phosphorescence. So from this data, we had the triplet energy, we had the singlet energy, we know it's emissive, and that's basically all we need to let us know that this is a good material for upconversion. So again, got in the lab, or this time my student got in the lab and made a variety of compounds. So these are all derivatives of DPND. I'll go over why we did this sort of different generations of synthesis in a second, but just to look at their optical properties, they have, again, tunable properties, which is we like. And then by combining them with that same palladium phthalocyanine sensitizer, gratifyingly so, they all worked for upconversion. And so to quantify how well upconversion was working, in this case, we just did simple upconversion quantum yield measurements. So if we look at these first 6 derivatives, we can start out with the first compound. The first compound is just our base DPND. It has just these simple hexyl alkyl chains. It's the base molecule we can think of. And then we measured the upconversion quantum yield. And what we got was this number here, which is 0.29%. I should mention this is out of 50. And this is the pure upconversion photoluminescence that we measured out. We then took a correction factor. So this UCG you see here takes into account any sort of reabsorption losses in our measurement system. We're using a short pass filter. So there's a lot of wavelengths that we're cutting off with that filter. So we have to take into account reabsorption losses. And then finally on the right, this is a sort of standardization method that you'll see in upconversion literature, where you extrapolate the data to the maximum power, or to infinite power. In this case, we can compare data from group to group, and so we don't have to all be using the same laser. We can just imagine we're all using infinitely powerful lasers. So with this, this right-hand column is how we can compare to other groups. So this data was nice. We got material that did upconversion, that was it was visible. You could see the cuvette glowing yellow-orange in the lab, so that was nice. We wanted to see if we can make this better. So the first thing we did was actually taking some inspiration from groups here in Vilnius by doing a strap on that molecule. So instead of having the alkyl chains off to each side, we linked them together like this. And so that led to a pretty dramatic increase in the upconversion quantum yield. And the reason we think this is because we're relying on these sort of collisions to get triplet energy transfer to happen. If you have these two alkyl chains dancing like this, the chance that the alkyl chains hit each other and these molecules just bounce off each other is quite high. Whereas if you have the alkyl chains strapped on one side, you leave one face of the molecule completely exposed, and therefore energy transfer is much more likely to happen. The next thing we did was just going off to base molecule number 1 and add phenyl groups onto it. And again, we saw pretty dramatic increases in the quantum yield. So this was a bit puzzling to us at first, but then we tried to think about how this could be happening. And there's been this suggestion about how the triplet actually sits on the molecule. So for this, I was actually teaching my introductory organic chemistry lecture to my 200 students at UC San Diego. And actually from that, I thought of this because we were talking about resonance structures. So I'm not sure how many of you have been taking organic chemistry, but you can actually think about how you move these bonds around to make stable structures, and we can think about resonance structures. So on the left is the typical DPND molecule, but if you homolytically break all of these double bonds, you can actually get this structure here on the right. And what this tells us is that there's certain positions at which the radicals want to sit at in this diradical form. And you can imagine that you want a diradical in a triplet because you have these spins that are going in the same direction. And for me, it made sense that they want to be quite far away because you want to minimize this, this repulsion. Lucas, my PhD student, who you all know, also did some calculations, and this sort of qualitative assessment from the resonance structure was also backed up by the calculations. And one other nice thing about this sort of controlled synthesis that we do is that we can test these other hypotheses as well. So in addition to having the phenyl groups at the position that we think the triplets are at, or sorry, the diradicals at, we can also move the phenyl groups to positions where we don't think they're at. And we can see that while that does have decent upconversion photoluminescence, having the phenyl groups blocking where we think the radical is leads to much higher upconversion photoluminescence. So we think that this is the reason why adding groups to these positions leads to brighter materials. So moving forward, we thought, okay, let's see if we can add some sort of alkyl groups on these phenyl rings and see what happens. That led to lower upconversion quantum yield, unfortunately, but it did give us a much more soluble species, so we thought we could move forward with this. And so our next thought was, okay, if the strap leads to higher upconversion quantum yield and the phenyl groups lead to higher upconversion quantum yield, let's make something that has a strap and has phenyl groups. And then that wasn't quite good enough. So we looked into the literature and we're wondering what was happening. We do have a more efficient material, but not as efficient as we'd hoped. It actually turns out that the quantum yield, just the fluorescence quantum yield of this material is quite low. It looks like the strap length is highly dependent on the groups you stick onto it. If you have these phenyl groups on it and you have this strap, with only 8 carbons, you still have a sort of contorted shape for your DPND, which leads to lower photoluminescence quantum yields. So we could then just make a longer strapped alkyl chain that gave us a higher photoluminescence quantum yield, and we get very high upconversion quantum yields. So again, I mentioned that we need this right-hand column so we can compare our numbers to other people's numbers. And that was nice because we could compare our annihilator, compound 6, to the most common infrared to red or visible annihilating material, and that's rubrine. And that has an upconversion quantum yield, infinite upconversion quantum yield of 5.7%. So we are pretty happy with those results because they show us that just by looking at how we can very carefully tailor our synthesis, we can develop some sort of design rules to make more efficient materials even better than the existing materials that all groups are using. So I mentioned applications, and one of the big things that we were looking at back in grad school was how we can take our materials that we've developed, our new materials we've developed for upconversion, we can apply these to new applications. And so for that, we got on the topic of photoredox catalysis, something that Makeda talked about earlier today. And so I won't go so in depth because I'm not an expert quite like Makeda, but photoredox catalysis has really been this, this new emerging field of photocatalysis and has really revolutionized organic chemistry, at least in my mind. And so rather to these sort of 2 electron transfers that we're used to in organic chemistry, I don't know if you remember just pushing an arrow, thanks to photoredox catalysis, we're doing 1 electron processes, and that completely changes the synthetic toolbox. And that's been allowed by these sort of organometallic complexes such as this iridium catalyst here. So these are great, fantastic materials that have allowed this huge application or huge reaction scope to be opened up, but there are some drawbacks. So if we look at these photocatalysts, such as this ruthenium photocatalyst, it requires UV or blue light excitation. And that can be unfortunate if you're trying to do some sort of in vivo applications. So let's say you want to do photoredox catalysis within a tissue. Let's say, I think our dream application of this would be some sort of targeted photodynamic therapy. So if you have some sort of inactive drug precursor in the body, with light, you could activate it at a local site, let's say a tumor cell, a tumor. However, that's not really going to happen if you're using blue light or UV light to excite your catalyst because your skin has developed and evolved over the years to efficiently block out UV light because UV light can damage proteins. A fun little demo, I think we have some time. Everybody want to take out their phone cameras? If you turn on your phone flashlight and then stick it to your finger, put your finger over the flashlight. So then my question is always, which wavelength of light penetrates tissue the deepest? So which color do you see? Yeah, see red. And that's because the white light of your phone is emitting all of the wavelengths of the light, but only the red ones are penetrating. So what that tells us, if we want to do some sort of in vivo applications of upconversion, or sorry, not of upconversion, of photocatalysis, we should move towards red light activated processes. And so to us, studying upconversion, we thought, okay, let's just do upconversion in situ, and we can turn red light into blue light or UV light in situ to drive these chemical processes. So to do that, we went to just some base model reaction, the sort of alpha bromohydrogenation. So where you take this bromocetophenone and turn it into acetophenone. And so this has been done in the literature with ESNY, your photocatalyst, the DIPEA, that's your sacrificial reductant. In this case, we do it at room temperature, and then we use red light, so infrared light, 730 nanometers, and then we had our sensitizer and our annihilator. So rather than using blue light or visible light to excite our photocatalyst, we added this upconversion solution to make that visible light. So we then ran these sort of controls on the reaction. So all these things together, I was actually a little bit pessimistic about this the first time because we're adding so many things into a vial. But gratifyingly, we actually got quite high yield of chemical yield when we have everything together. We then did the controls, so removing one part at a time. So if you take out the ESNY, or the photocatalyst, your yield drops to essentially a negligible yield. So you need that photocatalyst in order to do this. If you take out the annihilator, you're not making visible light, so again, your yield drops to essentially nothing. If you take out the sensitizer, there's nothing to absorb that infrared light, so again, no yield. And then if you have no light, you have no energy, no reaction. So it shows that this process is actually occurring as we'd hoped. And so what we thought about this was, okay, we can show that we can use upconversion to do photoredox catalysis with infrared energy light. But let's move past the simple hydrodehalogenation. Let's move to an oxidation. So we can do simple oxidations. We can do simple reductions. We can do simple cyclizations. We can make carbon-carbon bonds now. So it's a pretty broad reaction scope that's available to us. And we also thought, okay, rather than doing near IR to yellow upconversion, maybe we can switch the sensitizer and annihilator pair. So here you can see we've switched our sensitizer and we've switched our annihilator. And now we can go actually up to blue light that we can generate. And this allowed us to explore even more reactions. So we can do this sort of Perol cyclization. We can do this 2+2 cyclization. And then we could even do polymerizations. So basically the entire applications or the entire reaction scope of photoredox catalysis is available to us if we use this upconversion system. So what was nice about this last reaction here was that we could use it to diagnose, as a diagnostic tool to see if upconversion was happening. So if we added this dimethacrylate crosslinker in that 5% there, we could actually make a cross-linked polymer. So what that meant was that after we did our reaction, we could flip it over to see if it worked, because we could make this cross-linked gel. And so what we did from here was we tried to see various barriers that our light could or could not penetrate. And then if our vial turned into a gel that was solid, it worked. So what we did here, you can see behind this very unsafe laser setup, you can see here on the left is our reaction mixture. And in front of it is actually a solution of ruthenium tris bispyridinium, a very common photoredox catalyst. And even when we blast it with blue light, that very dilute solution of that photocatalyst is absorbing all the light. So it's acting essentially as a block. So what that tells us is that even when we're using blue light in photoredox catalysis, having a photocatalyst that absorbs so strongly is actually hurting you in a way because it's preventing light from getting all the way through your reaction. And so we wanted to see what sorts of barriers we could and couldn't penetrate. So we had some fun with it. We went down to the corner shop back in New York where we were doing this. We bought like an ice cube tray. And then there's actually like a polysilicone cover. We put that on top of the ice cube tray, filled the ice cube tray with our mixture, and then we could actually see that we could penetrate through that polysilicone cover and make these nice X's and O's. We tried to use it as a tic-tac-toe set, but the safety people got really mad at us, so we had to throw it away. Again, for in vivo applications, we also wanted to prove that we could penetrate tissues with certain lights and not with others. So here you can see, I'm not sure if this is the best proof, but I'm not a biologist, so we thought the best tissue mimic for human tissue that we could come up with is just pork. In this case, it's bacon. You know, it's some fat, some water, some muscle tissue. And then we actually just wrapped our vial in bacon. And so you can see here the remnants of that 730 diode. So that's the infrared diode. You can see the very tail of it. And it's you can see it on the bacon. And then it would penetrate through. And we can actually generate the gel through that bacon, which was pretty nice. It shows that we can actually do this sort of in vivo catalysis with this technique. And probably my best control reaction I've ever run in my life was we wrapped the vial in bacon and then used the control experiment where we shined a blue laser on it. And this reaction on the left-hand side where we made the gel, it took about 30 minutes or a couple hours. We would leave it just to be sure. This reaction, we actually didn't go to completion. We didn't let it go for the full 2 hours. And that was because as soon as we left the lab, we noticed that we could smell cooking bacon, and you can see that the focus laser is actually cooking the bacon at that burn mark. So you can imagine if you're trying to do this catalysis within some sort of body like your own, you don't want to shine a blue laser that's cooking your skin. So again, this shows that this sort of application that we developed is quite useful. So that's the conclusion of my scientific work. I think the overarching picture, I think, is that we as synthetic chemists we can leverage our skills to develop molecules and design rules to make better materials for upconversion. So not just using existing materials, but rather developing new ones that are more stable, such as the DPND or the DPP, but also developing design rules on existing molecules to make them better. And then finally, I think that shows that when we have these new materials, we can really open the door to a wide variety of applications. So not just the ones that exist, new ones, as well as optimizing existing applications. I think there's a lot of work to be done in this field. There's a lot of great research being done, but I think there's much more we can do. In terms of challenges for the students that might be in the audience, I think there's a couple that stand out to me. So one would be moving into the infrared. I think it should be really important to develop new families of annihilators to push the wavelengths of light that we can use as input light. I'm using what I call infrared light, but it's really only near infrared light. If we can go farther and farther, 1,000 nanometers, 1,500 nanometers even, we can really start to improve the applications that we use. Another thing would be to increase the anti-Stokes shift. I mentioned briefly that this is something that we need to look at. It's something that I'm looking at in the lab currently, but I do think we should really look at tailoring the electronic states of our materials to maximize this anti-Stokes shift. And then finally, I think optimizing solid state upconversion is a big thing that we need to look at. I did all of my research so far in solution state, where upconversion is quite efficient, but as we move to the solid state, there's all these sorts of intermolecular effects that start to lead to less efficient upconversion that I think needs to be overcome. And so with that, I would like to thank the people that made this work possible. So for the work from my PhD, that was primarily under the supervision of now Professor Dan Congreve at Stanford and Professor Luis Campos at Columbia, as well as our collaborators Tom Rovis and Ben Ravitz, or sorry, now Dr. Ben Ravitz, both at Columbia for the photoredox work. I'd also like to thank my nascent group at UC San Diego. The work that I talked about was primarily led by talented master's student Alex Lyons, as well as with Lucas and my very good undergrad, Simon. And so before I end, I know this is a conference for students, and so I would like to let you all know that UC San Diego Graduate School is always looking for talented scientists. If you want to scan that QR code at some point, you can see all about us. So some key factors I want to point out, the stipend is ever increasing at UC San Diego. It's up to $44,000 per year, guaranteed funding. Fees and tuitions are paid and guaranteed, even if you're an international student, so you don't have to pay for anything. You only need a bachelor's degree to apply for the PhD program. You don't need a master's degree. And if you're interested in doing this, please come talk to me. Applications are due in December to begin a PhD in the fall of 2025. UC San Diego is a modern university. This is just pictures from my recent lab. We have a really large faculty that does all sorts of research. So basically any sort of research you're interested in is being done at UC San Diego, and we have the nice facilities to do that. Very collaborative, very interdisciplinary. And I think one thing that's also very appealing is that UC San Diego is extremely beautiful. So this is that library that I showed in that picture before. My building is right here. Alicia Keys lives somewhere over here. And there's this beautiful beach here in La Jolla that goes all the way down there for, 50 kilometers and all the way up for another 100 kilometers. So yeah, 20-degree weather year-round. It's a nice place to live. Yeah. So yeah, thank you.
Thank you, Andrew, very much for a beautiful and very clear presentation. So now the paper is open for discussion. Questions are welcome.
Running these photocatalytic reactions with your upconverting system, what is the ratio photocatalyst, your upconverter, how much it can influence the actual reaction inside, and how applicable it is into real world scenarios?
I don't think we did I don't think we did any sort of measurements or tailoring the efficiency the system based on how much annihilator, how much sensitizer. Rather, what we did was we looked at the most efficient photocatalytic system, the most efficient upconversion system, and just mix these together. So typically these upconversion solutions, you have sensitizer in the roughly micromolar range, the annihilators in the millimolar range. So these are actually much less concentrated than the photocatalytic systems. You know, these reagents are also like maybe 100, like 0.1 molar or something like that. So it's much less of the upconversion solution.
Okay, thank you.
Yeah.
Yes, more questions, please?
Thanks for your lecture. So you started from solar cells, and okay, what do you think about perspectives of possibilities still to enhance efficiency of silicon solar cells?
Yeah.
And what processes limits? What processes are the major obstacles to do it?
So silicon solar cell, I think the big thing that's still lacking is we don't really have an annihilator that can take the light that's far enough into the infrared. Because a silicon solar cell, depending on which kind you're using, you know, you're going to be around 1.1 EV band gap. So you need the light to hit your material, to be below that material, to excite the sensitizer, to then populate the triplets on the annihilator. So we definitely need new materials for silicon. I think the existing materials we have, with a little bit of tailoring, we can probably work on gallium arsenide already. So I think there's definitely possibilities there. And then after that, there are engineering challenges. So solid state is going to be an issue to have really efficient. You would imagine you'd want this to be solid state, not just have like some sort of solution behind your solar cell. So engineering that upconversion system to be efficient in the solar cell would also be a challenge.
Okay, over here.
Thank you for your lecture, and thank you for solving this bacon problem. So, this bacon is messing our reactions all the time. So, I was wondering, just so the concept itself was very nice. So you did some reaction with IR by upconverting the light,
Yes.
and in principle, like indirectly using blue light, let's say.
Mm-hmm.
And also all biological applications, they are very clear to me because of this penetration issue. But when it comes to chemical applications, how positive you are for the future of this method, given all the, you know, if you count everything. So if you use blue light, perhaps you have less losses because you're kind of directly excite your molecules. Also, affordability of IR sources as compared to typical LEDs. So do you think there might be cases in real life where this would be advantageous?
From like a chemical standpoint, I think you could think of it as another, like, so I didn't show this, but we actually ran some control reactions where we could take out the photocatalyst, the ruthenium photocatalyst, and by having this singlet excited annihilator, this could actually do some sorts of reductions in oxidations. So if we take out that photocatalyst, you've already have some less energy transfers you have to worry, less components you have to worry about. This is still like a 2-photon system, so there's some energy losses there. But you can imagine if you're doing this sort of 2-photon excitation, essentially, you can probably break stronger and stronger bonds if you're taking this energy together. So maybe if you tailor the right upconversion system where you have an annihilator that emits into the UV, you can start to break very, very difficult bonds. I think there's some work from Christoph Kirsig in Mainz, I want to say, who's looking at this with these like UVB annihilators to break very, very strong bonds.
Okay, any more questions? Okay, maybe I'll ask one question. So as far as I understand, most of your results were obtained upconversion in solutions. So I'd like to extend and also the question, so how you see your annihilators and the upconversion system will act in a solid state, and what do you think, how do you want to cope with this problem, like the high concentrations of annihilator, you will need to somehow to get rid of the quenching, concentration quenching, and then but on the other hand, you'll need to maintain the TTA, so the depth energy transfer, so all these complex things that come begin to play in the solid state.
Yeah, this is a huge challenge. I'm not sure if like pure solid films is the way to go. I think there's a lot of great work being done on looking at like matrices and gels and things like this, where you can control the intermolecular distance between these things, right? Because a lot of these materials, they're heavily conjugated. So if you're going to get them right next to each other, you're going to have H aggregates, J aggregates. You're going to have all sorts of excimers, and this sort of excited state dynamics are really going to be deleterious to the upconversion process, in my mind. So I think carefully controlling this, the distances between chromophores, I think is going to be very important. People are trying, not super successfully so far, but I think this is, in my mind, this is the way forward.
Okay, thank you. Any more questions? Okay, if that's not the case, though, thank the speaker again. Okay, now we'll have a short break of 15 minutes and then the